will take longer to board the passengers, so the schedule has to be such that the first bus arrives at 4 and then it will take 6 minutes to board all the passengers and then it leaves. And if the passengers arrive in a uniform rate, as it's predicted by Newell and Potts, this line here, everything works fine because the intersection between the boarding line and the arrival line is exactly at 10, so there is no problem. But if we use this timetable when the arrival of passengers is not uniform, then we have problems. And the reason is that at any time, the number of users predicted by our model is lower than that predicted by the uniform arrival model. So this means that when the first bus arrives, it will have less passengers to board, and the consequence is that it will leave much ahead of the scheduled departure time, and so this earlier departure triggers bunching. The second scenario that I want to show you is the case in which we have, again, no exogenous delay. We study two situations in which the boarding rate is the same, but we have, in one case, the overall demand is lower than the one used to plan the system, and in the other case, the overall demand is higher than the one used, larger of the one used to plan the system. And you can see again that there is no bunching according to Newell and Potts, because again there is no exogenous delay, but our model does predict bunching, both when the demand is lower and when it is higher than the planned one. And so I think the second message is that bunching can arise if there is a mismatch of between the planned demand and the actual demand, and this and bunching can occur for values of demand both lower and higher than the planned. The reason for this can be easily understood again if we look at these curves here, because basically if we keep the boarding rate constant, means that this line stays the same, but if we change the overall demand, so the total demand, that means that this line, the green line, will rotate around this point. And so, of course, if the demand is lower, the first bus will leave earlier. If it is higher, it will leave later than scheduled. Third situation, in this case, we analyze what happens if we have exogenous delay. So the situation in which even the model of Newell and Potts predicts, also the model of Newell and Potts predict bunching. So we studied two cases, same boarding rate, same total demand, but we have a relatively small delay here on the left-hand side and relatively large delay here on the right-hand side. So the bars in this slide are basically, they represent the average of the absolute deviation of the headways calculated over all buses at each stop. So what we can observe here is that, of course, if the delay is larger, also the bunching condition are worse, as of course this is what we expect. But then the interesting part comes when we compare our model to the Newell and Potts model, because you can see here that the perturbation under the non-uniform arrival of passengers are smaller than those for the uniform arrival of passengers for the first bus stops. But then the situation becomes the opposite, and we can see here that if the arrival rate is not uniform, the system will perform worse in a worse way than if the arrival of passengers is uniform. And then we can also see here that the difference between what happens with the uniform arrival and non-uniform arrival are larger when the delay is smaller. In fact, you can see here that the two bars tends to have the same height. Here we see instead the bars here are they represent the value, the average value of the absolute deviation calculated for each pair of buses over all stops. And so in a sense, what we saw in the previous slide was the evolution of the phenomenon in space, of bunching in space. What we see here is the evolution of bunching in time. And we see, I mean, basically the main message is the same that we get from the previous slide. So that's the system tends to underperform under non-uniform passenger arrivals, where tends here means that in time and in space. So we have that the system underperform for at stops farther from the one where we had the delay, and for time more distant in time from that one where the delay happened. Finally, we explored what happens to bunching when the passenger perceptions about the system reliability change, or when the passengers' preferences regarding to waiting time changes. We have compared 5 cases. So the first 2 cases are the cases that we have seen so far, so the uniform arrival and the what we call the basic demand case. And then we have studied also what we call the unreliable system case, the weight-averse case, and the early departure case. So let's see what are these cases. So in the remember that in the basic scenario, the passengers expect a departure that departure are possible from 1 minute before the scheduled time to 2 minutes after the scheduled time. Instead, in the unreliable system case, we consider that departures are possible from 2 minutes before the scheduled time to 4 minutes after the scheduled time. So this means that basically the information that the passenger has is less accurate, if you want. So he cannot trust that much the information that he has, and so you can see here that the arrival. So of course, this the curves on this plot they represent the arrival processes. So the curve representing the arrival process in the case of an unreliable system tends to be more similar to what you have in the uniform arrival, because remember that the uniform arrival is what we expect when the passengers do not have any kind of information at all. So if the information is less accurate, of course the arrivals will be closer to what happens in the case in which we don't have any information at all. Then we have what we call the weight-averse passengers. So in this case, we have increased the parameter alpha, which represents the aversion of passengers to waiting, basically. And what happens, as you can see here, is that passengers tends to arrive concentrated at an instant close to the expected departure of the bus. And then we have the last case, the early departure case, in which again we have a high value of weight aversion, but in this case basically we consider that the passengers, they fear only earlier departure, and they assume that the bus can depart up to 8 minutes before the schedule and no late departure. So of course we know that this is a bit unrealistic scenarios, but we wanted to understand what is the consequence of having a curve of arrivals which at certain times is higher than the prediction given by the uniform arrival model. So the conclusion that we got from this experiment is that the worst case is the case in which we have the weight-averse passengers, because in that case, even for small values of exogenous delays, we have very, very serious problem with bunching. This is a bit worrying, if you want, because the weight-averse behavior is what we expect if we provide real-time information on bus departure, because if we provide real-time information, of course we expect that the arrivals of passengers will be concentrated close to the announced departure time. So a situation like similar to the one shown here with the red line. And so given what our model says, we can conclude that the real-time passenger information may worsen the system performance in terms of bunching, of course, in case of unexpected delays. So conclusions, we have developed a bus bunching model considering non-uniform passenger arrival patterns at stops. Under our assumption that there is no holding strategy, because as I said, we assume that the bus will leave the stop as soon as all the waiting passengers have been boarded. The operator should carefully assess the demand and the passenger arrival patterns, because if there is a mismatch, as we have seen, in the between what has been planned and what happens in reality, we can have serious cases of bunching. There is a large body of literature dealing with policies to reduce bus bunching, but almost all of this literature considers uniform arrivals, so we should revise this literature should be revised considering what we have shown with non-uniform passenger arrivals. And then finally, given the conclusion that we had we saw at the end with about the what happens in case we have weight averse passengers, if the operators thinks that they cannot guarantee on-time arrivals and departures, then they should try to smoothen a bit the pattern of arrival, the passengers' arrivals. For instance, by making notes to the schedules that slightly early or late departures are possible, so in a sense decreasing the confidence of the passengers in the information we provide. Further work, how we can expand how we should expand this work. Well, first of all, as I said, one of the motivation was the fact that nowadays we have real-time information. So if we want to take into account the impact of real-time passenger information on bunching, we need to study what is the effect of upstream bus delays on downstream passenger arrival patterns. In this case, we studied, we assumed boarding as an unsaturated process, but of course buses, they have a limited capacity, so we should include in the model bus capacity constraints, which will have effects both on the supply side and on the demand side. On the supply side, of course, we will have we may have a reduction of dwelling times because of course the bus cannot stay there forever, but when it is full it will leave the stop even if there are still passengers waiting. But at the same time we'll probably observe slower boarding rates when the level of occupancy is higher. On the demand side instead, well, there is the problem that when we consider capacity, there are different levels of comfort for the passengers depending on the level of occupancy of the bus, and this may change the utility function. But we can also expect time-dependent risk aversion because some of the passengers may try to avoid the busiest services. So we expect the consideration of bus capacity constraints will give us non-banal insights on the problem. Then, so far we have assumed non-constant constant boarding rates, but of course the boarding rates in general are stochastic. Plus, we should take into account that we have at least 3 classes of passengers in general. So passengers using, at least in Edinburgh for sure, we have 3 classes of passengers. So passengers using a smart card, which can board very fast. Then we have passengers buying tickets on board, and they have slower boarding times. And then we have passengers with disabilities. Of course, boarding, let these passengers on board, of course, takes a lot of time. So all of these categories should be considered in the bunching model. We should improve the bus propagation equation to deal with overtaking. And finally, of course, we need a better understanding of traveler behavior. For instance, in terms of specification or of calibration of the time choice model, or the number of the buses which passengers do actually consider when they decide the arrival time at a bus stop. A few words on what we are doing at the moment. Basically, we are further studying the impact of passenger behavior on bus bunching from 2 points of view. First of all, we are considering what is the impact of passenger behavior on overtaking, because of course if you have only one bus at stop, all the passengers waiting for the bus will board that bus. But if you have, when the first bus is at a stop, a second bus arrives, then you can have in general 3 scenarios. In the first scenarios, most of the passengers still in the queue go to the second bus. You can have the case, so in this case what happens is that it will take longer for the second bus to get all passengers on board, and so the second bus will depart after the first one, so there is no overtaking. There is the case in which the queue splits exactly in half, and so in this case the two buses will leave the stop at the same time. And then there is the last case is the case in which most of the passengers will stay in the original queue, and so the second bus can depart after the first one. So in this case, we need to we will observe overtaking. So we are studying how this parameter gamma, which describes how passengers in the queue split when the second bus arrives at the stop, affect bunching. The second thing that we are studying instead is the interaction, let's say, between passenger behavior and common lines. So when you have public transport services, you can have a situation in which, as the one that, shown in the picture here, in which you have basically the two lines, the blue one and the red one. At a certain point, they become parallel and they serve the same corridor. So we call this a case of common lines, because passengers may choose one of the, either of the two lines. So basically, what happens is that we can. So our problem starts from the consideration that some of the stops of these two lines here can be designed as a common line stops, which means that the stop are located exactly the same position, and other stops instead might be maybe not common line stops, which means that they are close to each other but not exactly at the same position, the same location. The difference is that in the former case, well, in general, when we have common lines, we have three groups of passengers. Passengers waiting only for the blue line, passenger waiting only for red line, a passenger for which both lines are fine. So if a bus is designed as a common line, as a stop is designed as a common line bus stop, then when the bus arrives there, the red bus arrives there, both the passengers waiting for the red line only and the passengers waiting for either the red or the blue line will board the service. But when we have non-common line stop, then we'll have that the passengers have to decide in advance if they want to board the blue line or the red line. And so in this case, only the passengers who have decided to board the red line will be able to get on board. So what we are doing at the moment is to analyze how the design of stops of common lines affects bus bunching, basically. So this concludes my presentation. So I'm now very happy to take over all of your questions. Not before pointing your attention to this very nice song from the Hollies. I don't know if you know it. It's called Bus Stops, and it talks about this love story started at a bus stop. And they say it's silly, but it's true, thinking of a sweet romance beginning in a queue. So this means that, well, actually, passengers may have different perspectives on what happens in the public transport system, and for sure, if we want realistic results, we need to take this different passenger perspective into account in our models. Many thanks for your attention.
Thank you, Dr. Fonzone. It's a great presentation, and also thank you for the ending sweet story. All of you, please feel free to raise your questions, and if you have it right up front, you can just speak to your microphone. I think I've already unmuted all your guys on my end, and you can unmute yourself. Make sure that you want to unmute yourself before you raise your question. Or there is a chat box. If you want to take a little time to organize your words, you can use the chat box. But when you send it out, make sure that you select send the chat to organizers and panelists only. Again, organizers and panelists only. Sure, please feel free to raise your questions. Okay, so Dr. Fonzone, while others are organizing their thoughts, I like to, ask something. Probably I missed some part of your presentation. I was actually organizing the panel, so I see that the basically the passengers' behavior depend on buses' arrival patterns, but actually the buses' arrival schedules are also affected by the passenger arrival sequences. So they're like a chicken and egg in your model formulation. Did you consider this kind of like interdependence between passenger arrivals and bus departures?
Well, thank you for this question because it gives me the opportunity to underline again a basic assumption of our model. So the basic assumption in our model is that the passengers will decide their arrival at the bus stop depending on the perception that they have of the bus departure times. So basically, this function here, these functions, let me go to the slide just a second. So these functions here are the perceived departure time, the probability distribution function as perceived by the users. So the idea is that the passengers know the schedule, but they do not completely trust the schedule. So they, for instance, in this case, for the bus one, the blue bus, they think that this bus may depart in any instant between in the interval between 2 and 6. Of course, each instant has a different probability of occurrence, but they don't know what is the actual departure time. And then instead, so this is what happens, if you want, in their mind. And then we have what happens in the real system, so as a consequence of their behavior. And of course, their behavior changes the actual departure times of the buses, because the buses can only leave after all the passengers waiting have boarded. But basically, the passengers will still base their arrival time not on what the current situation, the network, but according to the knowledge that they have of the timetable, so according to these functions. So at the moment there is no feedback mechanism, if you want, to take into account the fact that the passenger's behavior change the arrival time of buses at bus stops. But this is one of the next steps that I was describing before, because I mean, of course, we want to understand what's the impact of real-time information. So if you introduce real-time information in the system, of course, the passengers will know. So we'll have to update, let's say, these functions here, depending on the information they get from the real-time information. I don't know if this makes things clearer.
Yes, very clear. Yeah. Yes, I completely understand now. And I remember you mentioned the real-time information in one of your last few slides. You know, that's going to be a really neat way to address these interactions. So,
Completely agree.
okay. All right. Is there any other questions from the audience? Okay. If not, then finally I thank Dr. Fonzone for his interesting presentation, and good luck to the future studies, and thank all of you for attending this webinar series. And next one will be scheduled next Friday about the same time, and I will send you the announcement very soon. And I hope all of you have a good weekend. So the webinar adjourns.
Thank you very much.
Thank you.
Thank you.
Bye-bye.